Hello. What I'm going to do right now is just go through lab number 3, creating various graphs with you. So some of you might be a little late in completing this lab. So if you are still working on finishing this, why don't you follow me through it? And as I'm going through this, you go through yours as well. Okay? So let's just start this lab thinking about where we see graphs in our everyday life. You see graphs, whether you think about it or not. Where I often see graphs are places like my weather app. Okay, I see graphs when I'm checking out the weather for the day. Okay, it usually gives me a temperature graph, maybe a humidity graph, maybe how much wind or rain we're gonna have. So my weather app, definitely a good place to see graphs. I also see graphs when we're talking about the COVID-19 pandemic. Okay, every time people talk about this, there's usually accompanied by a graph. Where is it increasing? Where is it decreasing? What places are in bigger trouble than other places? Okay, so those are two big places right now where I tend to see graphs. Okay, just know that you're going to see them out in the wild, whether you realize it or not. Graphs are everywhere, and the reason why they're everywhere is because they're really, really helpful. Okay, it's a really good way of showing information and how that information changes over time. The first procedure here, the data table below shows the average date of the first breakup of ice on the Tanana River in Nenana, Alaska. Latitude 65 degrees north, 149 degrees west. The average date of the first ice breakup is shown for the 4 decades. So here we have a data table with decade in this first column, the 60s, 70s, 80s, and 90s, and the average date of first ice breakup. This is the average date in that decade when the ice first started breaking up on that river. On the grid provided, construct a bar graph of the average date of the first ice breakup for each decade shown. So on our bar graph now, we have our 2 axes. We have our x-axis along the bottom and our y-axis along the left side. And what we have to do is just graph the information here. So in the 1960s, our first ice breakup was May 7th. So in our 1960 column right here, we're going to go all the way up to May 7th. And we're just going to create a bar graph. We're going to create a bar right here. Okay. Bar doesn't have to be pretty, but it does have to be legible. Okay. So now what this is telling us is that in the 1960s, the first date of ice breakup was May 7th. In the 1970s, it was May 5th. So in our 1970s column, we're going to go up to May 5th and create our bar. In the 1980s, it's May 4th. So in the 1980s column, I'm going to go up to May 4th, and I'm going to create my bar. In the 1990s, we've got a pretty big jump here. In the 1990s, the date of first ice breakup is actually April 29th. So I'm going to go, April 29th is over here. So I'm going to go up to April 29th and create my bar. If you missed any of that, this is a video. Feel free to go backwards in the video and rewatch. Moving on to number 2, the data table below shows the hardness of the minerals talc, quartz, halite, sulfur, and fluorite. This is measured on the Mohs hardness scale from 1 to 10, where 10 is the hardest and 1 is the softest. So here we have our 5 minerals and their hardnesses. On our graph over here, we have our 5 minerals on the x-axis and the hardness on the y. Talc has a hardness of 1. So here's talc. Here's 1. It's just one box. We're going to fill that up right there. Talc has a hardness of 1. Quartz has a hardness of 7. So for quartz, I'm going to go all the way up to 7 up here and create my bar. I'm just going to fill that in lightly. Halite has a hardness of 2.5. So I'm actually going to go up 1, 2, and then only half of this next box. I'm not going to fill up this next box. So we're only partially filling up that box right there to show 2 full boxes in 1 half box. Sulfur has a hardness of exactly 2. So we're going to fill it up to 2 right there, 1 and 2. And fluorite has a hardness of 4. So I'm going to go 1, 2, 3, and 4. And there's your bar graph. Great. According to the graph, which mineral is the softest? So remember, up here I told you that 10 is the hardest. So 1 is going to be the softest on the scale. Here we have a mineral with a hardness of 1, and that mineral is talc. Stop and think. Bar graphs are easy for reading the highest and lowest value in a data set. For example, by looking at your graph above, it's easy to see which bar rises the highest on the y-axis of hardness and which one rises the lowest. This makes comparing values very simple, but finding exact numbers challenging. Scientists don't usually use bar graphs to represent their data findings. Why do you think that is? And the reason for that is in this reading right here. The reason why scientists don't usually like bar graphs to represent their data findings is because scientists like exact data. We like seeing exact values, and that's really hard to see on a bar graph. So scientists like exact values, which are hard to represent on a bar graph. Okay. Again, if I'm going too fast, this is a video. Feel free to pause and rewind. Line graphs. The following data table shows the average number of days with thunderstorms that occur over land areas at different latitudes each year. On the grid provided, plot with an X the average amount of days per year a thunderstorm occurs over a land area for each latitude, shown on the data table. Connect the center of the X's with a line. So we've got 3 steps here. Step 1, plot the point. Step 2, turn the point into an X. Step 3, connect those X's with a line. So here we've got our data table. We have latitude, degrees north to the equator to degrees south. And here we have our number of days a thunderstorm occurs. So our first data point is 60 north. So I'm going to go down here and find 60 north. So here's our equator. This is north latitude because it says, and 60 is right here. And our number of thunderstorms at 60 north is 5. So from 60 north, I'm going to go up to my 5 and make an X. My next one after that is 45 north, and that has 14 thunderstorms. So I'm going to go to 45. I'm going to go to 14. So here I have 10, here I have 15. 14 will be right under 15. It's going to be right there. Next one, 30 north, has 19. Here's my 30. And again, 19 is going to be right under 20. 15 has 30, so 15 north. I go all the way up to 30, right here, and make an X. And 0 degrees, the equator has 56. So I'm going to go all the way up to 56. This is 50. This is 55. 56 will just be a little bit above 55, right about there. Now I have to continue to my degrees south. 15 south is 44. This is 30, 35, 40, 45, 44 will be right there. Mark that with an X. 30 south is 21. 10, 21. Mark an X. 45 south is 8. 5, 10. 8 will be halfway in between 5 and 10. And 60 is 0. So I'll just mark it X right there at 0. Okay. Now I have all of my X's. Now what I need to do is to connect those with a line. So I'm just going to follow and connect each of these points with a nice smooth line, peaking here at 0 and then going back down again. Okay, so there's your first line graph. Now we just do this a couple more times. The data table below shows the radioactive decay of carbon-14. The number of years required to complete 4 half-lives is left blank. On the grid provided, construct a graph that shows the radioactive decay of carbon-14 by plotting an X to show the percentage of original carbon-14 remaining after each half-life. Connect the X's with a smooth curved line. So if we look over here on our graph, we've got our number of half-lives, which is right here, and we have our percentage of original carbon-14, which is right here. We're not doing anything with time. There's no time on this graph. So I'm just going to put a big X for that. We don't need that, not for this graph. Okay, so now we just have to plot these. Number of half-lives, 0. Carbon-14 remaining, 100. Number of half-lives, 1. Carbon-14 remaining, 50. 2, 25. 3, 12.5. So here's 10, here's 15. It'll be halfway in between 10 and 15. 4, 6.3. So here's 4, here's 5, here's 10. 6.3 will be somewhere close to 5. The bigger your dot, the better you're going to be. Okay? 5 half-lives is 3. This is 0, this is 5. 3 is like right there. Again, the bigger your dot, the better you're going to be. And 6 half-lives is 1.6. Okay, that's very close to 0 down here. Great. So those are our dots for our line graph. Now we need to connect those dots with a line. So all we're doing is we're finding the value on the x-axis, finding the value on the y-axis, and plotting a point, just like you do in math. Okay, we have one more to go, so let's finish this up. The data table below shows air temperatures and air pressure recorded by a weather balloon rising over Buffalo, New York. On the grid, construct a graph of latitude above sea level and air temperature by following the directions below. Plot an X for air temperature recorded at each altitude. Connect those X's with a line. Again, here's our graph. We have altitude and we have air temperature. Altitude and air temperature. We are not doing anything with air pressure, so you can put an X through that. So now we just start altitude and air temperature at 300 meters above sea level. Our air temperature is 16. So at 300, our altitude is 16, all the way up there. At 600, our altitude is 16 and a half. So at 600, we're at 16, 17, 16 and a half is right there. At 900, we're at 15 and a half. Right there, 15, 16, so 15 and a half will be halfway. At 1200, we are at 13, which is right there. At 1500, we're at 12, which is right there. At 1800, we're at 10. At 2100, we're at 7 and a half. At 2400, we're at 5. And at 2700, we're at 2.5. Great. So we've got all of our points plotted. Now all we have to do is connect them with a line. So just go from point to point, connecting those points with a line. Remember, this is a line graph, not a dot graph. So make sure you're connecting all of your points with your lines. Remember, this was a video, so if you need any more time, just go back in the video and rewatch the section. Hopefully this was helpful, and I'll see you in the next lab.